Hey, math people. Fairly big day today. We're going to be studying the gradient factor. Oh, and then also the directional derivative. But the gradient factor. This is a big day because we utilize the gradient vector for a good chunk of the rest of the course. So saddle up for that. Or saddle up for the next lecture. That'll make sense later. Okay, what are we looking at today? We're going to be just looking at partials again because we need to understand the philosophy behind what the partial derivative does for us at a particular point. Use that to build into the directional derivative and then pluck out an ingredient of that to get the gradient. And then just study some key attributes to the gradient vector. This video is for you, Ricky. What does that mean? It means you should pause when you need to. Be patient with yourself. Use the timestamps, and I don't know, just let's do some math. All right, so we once studied surfaces in the context of just boring little partial derivatives. If I asked you to find the partial with respect to x, partial with respect to y, and then plug in 1 comma 2, you should get some numbers. See if you can do that right now. 3, 2, 1. All right. So what do these numbers give us? Ignore this drawing. Well, I'll talk about that in a sec. Well, the partials, they give you remember the idea behind it is it's the change of x while keeping y constant for the first and the change of y while keeping x constant for the second. If you were to plug in 1, 2, the idea primarily being, if I have the surface here and I have my point 1, 2, what I can do is I can just turn on the curve when x is fixed to be 1, which would be on like this plane. And what this would give you is this curve right here. And then we can turn this off. You can see it's a positive slope. This is the partial f, partial y. It's this 8. Okay. It's this 8 here. This 8. All right. And that's because this has a slope of 8. This curve has a slope of 8 when y is equal to 2. Now, if I turn the surface back on and I turn this off and I turn these two on, we can see here now we get change that is parallel to the x-axis here. So we'll look at the orientation this way because that would be the direction where x is positive on the right and negative on the left. And I can turn off this surface. Maybe even this as well. You can see here the slope is negative. It's a negative 4. So the idea behind this and the interpretation being that if I fix my y to be a constant 2 in this case, we would get a slope of negative 4. Okay, so what about the other directions, right? That's the big thing, is that I'm only studying these two very specific curves, right? But aren't there more directions? Yeah. Can't I travel in many different, so this is what I meant by this. Can't I travel in many different ways, like here, or here, or here, or here, or down here, or down here, or up here? And the answer is yes, of course. And do we have math for it? Double yes, of course. That one's without blinking, no brainer. Of course, we have math behind that. So that's what I want to show. So remember, what do the partial derivatives evaluated at these locations describe? It's that experienced slope perfectly parallel to either the x or y axis. There are more directions. So this is supremely limiting. It's like playing a over-the-top, like you can only move like a Game Boy Pokemon game, up, down, left, right. That's it. We want to be able to move in all the directions, right? Like an isometric, full, all 360, right? So keep that 360 in mind because angles are going to be a little important for that. So let's kind of build this idea. Is there a solution to this problem? Absolutely. It's called the directional derivative. So if f is, which, I just gave it some flack at the beginning of my lesson today, didn't I? But the directional derivative is a very useful tool. It just kind of starts and ends here, whereas the gradient vector, you keep going with that. So if f is a differentiable, so here's the directional derivative, okay? If f is a differentiable, there it is, and u is a vector that is a unit vector. So some ab, that's a unit vector. Then the duff of xy, d sub u of f, the directional derivative in the direction of u, is this f sub xy, so the partial derivative with respect to x times a being the first component of the direction that we're moving in, plus partial derivative with respect to y times the b direction that we're pointing in for this unit vector, which is secretly a dot product between the partial derivative vectors and then the unit vector. We're going to look at this idea later. Well, then at the end of the day, through this computation, you'll get a slope in that direction, the direction that u is pointing in. The better version of this, though, is just thinking u as cosine and sine, because if you think about the vector's magnitude, if you take the square root of sum of squares here, you do get a magnitude of 1, right? Cosine squared, sine squared, if you take the sum of that, that's just 1. Square root of 1 is just 1. So I tend to like this one a little bit more because theta can be thought of as the angle sweeping from, and I'll just kind of show it here. Theta can be thought of as the angle sweeping from parallel to x axis. So like if you had an angle of like say 60 degrees, which is pi over 3, it would be moving in this direction where my cursor is going, right? If you have motion, let's just say of like 3 pi over 2, it would be moving in this direction because 3 pi over 2 is the lowest point of the unit circle, so it would be going down. It would actually be like parallel to the y-axis, but kind of in that negative direction, I guess. So we have all these different motions. You can think of it. You can think of it. There's like a little circle here, and then you can go this way or this way or this way or this way. And then I prefer this approach because theta is easier to control over just like some arbitrary vector that's a unit vector. You'd have to go through the work to make it a unit vector sometimes. Okay, yeah, let's do some practice problems with this. So with the same function, so we're dealing with the same function. What I want to do is talk about the different slopes and moving in different directions here. So if we wanted to move in the direction of 3, 4. So as I'm this like orange particle here, and as I climb in this direction, what is this slope? Okay, so it should be a positive slope, right? It should be a pretty intense positive slope. Let's see it. 3, 2, 1. So the idea behind this is to take the partial derivative with respect to x, multiply it by the x component here, and then plus the partial derivative with respect to y, multiply by this second component here, 4/5. Surely this is a positive number because this number is bigger than this number. Where did I get this -4 and 8? I got this from the partial derivatives we found above, right here, because we're still studying this point 1, 2. Okay, so what about this next one in the direction of the not unit vector? So you do have to make this a unit vector and then do the same process. So you'll see this -4 and this 8 quite a bit. Yeah, so you're going to be rewriting a substantial chunk of this, but inside of each of these parentheses will be 2 different numbers. You need to make this a unit vector, so I'll give you a moment to play with that. 3, 2, 1. Okay, so to make it a unit vector, you have to take the square root of sum of squares. So you just get root 13, so you can divide each of these by root 13, and then you're just plugging straight into the formula. So I guess this would be pointing in the direction, so -2 and then 3. Yeah, so it'd be -2 square root of 13, and then 3 square root of 13. So it'd be climbing in this direction now. Okay. But now this is where the fun starts to kick in, because now I can just give you, let's just use the better definition for the rest rather than like having to find the magnitude here. I can just give you an angle. And then that way we always can use sine and cosine, which always create a magnitude of 1 by Pythagorean identity. So we're going to try out C here using this new formula in purple. So 3, 2, 1. Okay, so it's going to look like this. So consider how the cosine of pi over 3 is 1/2, and the sine of pi over 3 is 3/2. So what's actually nicer about this, so we know the direction this should point in, right? It's pi over 3, which is 60 degrees. So when I adjust this here, I should be pointing in the 60-degree direction. So see if you can kind of think about where this arrow is going to point as I kind of tell it to point in that direction. That should make sense. That's in that like pi over 3 direction if there was like a unit circle right here. So we're climbing in this direction, and it's still another positive slope. This is a bigger number than this. Okay, what about 4 pi over 3? Interesting. Pi over 3, 4 pi over 3. What's the relationship between those? Here's my hint. First one is uphill, and then 60 degrees counterclockwise, right? So we're going uphill in this direction, right? Positive slope should make sense. Well, I'll give you the hint here. So the other one is downhill, 240 degrees. So, this is 180 degrees in this direction. So what should we notice about the slope? We should notice something. All right, finally the answer, 3, 2, 1. You should get the exact opposite sign. You should get the exact opposite slope, right? Because if you have a slope, I don't know exactly what 4 root 3 plus 2 is, or minus 2 is. I don't know. Let's just say it's like 10. So if you have it's not 10, but let's just say it's like 10. If your slope was 10 going in this direction, then it should make sense that if I slap in 4s here in the exact opposite direction, it should be negative 10. So that's why we see the exact opposite slopes, right? All right, what about in the direction when theta is equal to 0? This should look familiar. And then in the direction when theta is equal to pi over 2. This should also look familiar. So see if you can conceptually solve this before you do the plug play, okay? 3, 2, 1. Hopefully conceptually you're just cool with the idea that this is literally just the partial derivative with respect to x, right? Because if I make this 0, and I make this 0, I'm at an angle of 0. I'm just going in this direction, which, like, hey, that's literally what the partial derivative with respect to x gives me. Perpendicular to the y-axis, sure. Parallel to the x-axis is the primary idea. So at a pi over 2, consider how at a pi over 2, this is secretly 3, 2, 1. This is secretly just the partial with respect to y, right? So we can replace these thetas with pi over 2 and pi over 2. And sure enough, that's just in that direction parallel to the y-axis. So if I were to replace this with theta, and replace this with theta, look at this. I can do a cool thing, I swear, watch. Wait, I'll do like theta sub 1, because I need to make it a variable. It'll be worth it. Trust, don't skip through this one. This one's going to be crazy. Here on a 2 pi. It's not going to be that crazy. But you can see here is that we're getting all the directions now. So this unlocks access to us moving. Oh, I mean, that's beautiful. Come on. Now I just got to get it. What would be the z height? Okay, so bringing this all together. You can see here if I hit play, these are all the different directions that my point can move in, right? I can move this full 360 now. Just kind of verifying this really quickly that this is in fact, this does just measure the slope of this blue line immediately from this orange point. Let's just look at, say, when when theta is equal to 0, right? We know that when theta is equal to 0, that should just crank out a slope. So this is what this s means. It just means the slope of -4, and that should make sense because we found when theta was equal to 0, the -4 was the slope, which was ultimately just the partial derivative with respect to x. You can see that the slope at pi over 3, we determined that was -2 and then plus 4 root 3. Well, that value happens to be 4.928, and sure enough, the slope is 4.928 at this moment. That's the slope of this curve. Okay. Good stuff. Directional derivative, very useful. We now can talk about change in every direction. Instead of just 2 directions, we now have every direction, an infinite number of directions. Okay, now that we're done with the directional derivative, let's move on to the gradient vector. So we've seen the vector of partial derivative used now twice. So we saw it once with chain rule, and then now we're seeing it within technically this -4, 8 that was dotted with either this vector or this vector or this vector with cosine and sine as the x and y components generally. So we've seen it so many times now. So here it is, right? This vector right here, the collection of the partial derivatives. Like I said, we saw it within Duff, and we saw it within the chain rule from lecture 1. We've seen it so much now. Let's just call it a name. Let's call it Del. Let's call it our friend Del. What? So here's why we call it Del. We have we throw this little upside down triangle in front of this vector. There in front of this f to call it a gradient vector f. And we also call it del f out loud in verbal language because it's like an upside down delta. So you can either call it grad f or the gradient vector or del f. Either of those are fine. And then we can keep adding terms and dimensions to create gradient vector in R3, R4, so on and so forth. Okay. So now this gradient vector has some important attributes, some important qualities. I want to demonstrate 2 of them right now. So what if we wanted to optimize our directional vector here, our directional derivative? Right, because I have all these different directions that I can move in. Surely one of these has the most intense slope, right? Is it here? Is it here? Is it here? What might it be? Well, if we look at the dot product formula for the direction vector, we have the gradient dotted with the unit vector. Well, there is a particular dot product formula which allows us to rewrite this as the magnitude of each of the vectors times cosine. Just normal multiplication. So if I wanted to optimize this expression, well, it makes sense that I would want cosine, one of the factors, to be the largest possible number. And the way that we make cosine of theta the largest possible number, well, it's just when theta is equal to 0 at this highest point. So the highest that cosine of theta can be is 1. So we can just kind of like ignore this term because anything other than 1 would make this expression smaller, right? Likewise, the unit vector, what's the magnitude of the unit vector? Well, it's a unit vector. The whole point of the unit vector is that it has a magnitude of 1. So this also just has a 1. So in order to maximize the directional derivative here, ultimately we're just taking the magnitude of del f, which would just be the magnitude of our partial derivative vector here. So in the case that we were just dealing with, the fastest slope at this value would just be the magnitude of the partial derivative value. So that would be square root of -4 squared and then plus 8 squared. So we'd be looking at a fastest slope of like 8.9-ish. All right, and then the other takeaway from this, though, so there's 2. So the magnitude of del f is the greatest slope. The greatest slope that you can encounter from climbing this mountain is a slope of that 8.94427 value. But then additionally, the gradient will always point in the direction of the greatest initial change. So if I were to just plot the vector pointing in the direction of -4 along x and 8 along y. So where did I get those values? I got them from here, -4 for x, 8 for y. This is the gradient vector at 1, 2, 2. That would then spawn us the direction of the greatest ascent. So take a look at this. What I'll do is I'll just turn on this little vector right here. It's in this direction. It's just pointing, hey, go this way. For the greatest ascent, so that would be, I don't know, like here-ish. Oh, wait, I'll try again. There-ish? Nope, missed. Like there-ish or here-ish. You can see that we're experiencing the greatest climb right around there. Which should make sense if I look at my slope number, actually. Let's try to get it to match. With that 8 point whatever value I had down below. If I try to get this to perfect match here, I think that's about the best I can do. You can see here that that's very close to this 8.9 value. I'd have to go maybe a little bit more. Oh, there it is. Oh, look at that. So yeah, you never will I exceed this value. This slope will always be like underneath that number. So let's practice this with additional context here. So here's an easier function to play with. We can see here that we have x times e to the y. So find the gradient vector, which is just a collection of the partial derivatives. Take the partial derivative with respect to x, take the partial derivative with respect to y, slap them in some vectors. That's all. And then compute f of 0, 0. What does this mean? 3, 2, 1. So the collection of partial derivatives should just be e to the y, because this is constant e to the y in front of this x. Derivative of a linear term is just a constant. And then this x is a constant in the eyes of y, so derivative e to the y is just e to the y, right? So, all right, we got ourselves the gradient vector. If we were to plug in 0, 0, what does this mean? So plug it in, get a number, think about what that means, 3, 2, 1. All right, so if you plug in 0, 0, you will get 1, 0. All right, So what does this 1 comma 0 mean? That is the direction of the greatest ascent. We have this, yoink, 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 yoink. All right, we have this surface here, which is x e to the y. So from point 0, 0, we have many different directions we can go. 0, comma, 0, comma, what is this going to be? 1, probably. Is that on the surface? Oh, it's not on the surface. 0, comma, 0, comma, 0. All right. We have many different directions that we can head in, right? I can go here, I can go here, I can go here. So the direction of 1 comma 0, so along the x-axis, is our greatest initial ascent. Initial ascent. So right away from the screen point, going perfectly parallel to the x-axis here, along the x-axis even, is the greatest initial ascent. Eventually it gets kind of faster over here, but initial is the greatest, the most important word there. So what is that slope going to be? Well, you just find the magnitude of this. So the slope is just going to be 1. So the read here is that if I climb in this direction of 1, 0, I will get the fastest rate of change in that direction. So you can see here at 0, 0, we actually work our way through all these different slope values depending on what direction we face. And you can see that the highest slope is, bam, very close. Bam, right here, when your angle is exactly 0 in the direction 1 comma 0. And we can play around with all these different positions as well, just for fun. So you can see here we can move this x value kind of along this curve. Here, we'll even do this. There we go. See all the different slopes in all these different directions just to get a better visual of what we're playing around with here. And this is just movement of that y. All right, let's move on to the last big application here. So now consider this paraboloid. What I want to do is take the gradient vector of it and then compute the gradient vector at all these values and then ultimately the slope at all these values. So remember, each of these outputs here would shoot out the greatest initial ascent at any of these points, and then these will be the slopes at those greatest initial ascents. So see if you can do the gradient vector first, and then plug in each of these points to get the direction at which we experience the greatest ascent. So 3, 2, 1. There's your gradient vector, your del f. So now do the directions here. So 3, 2, 1. So yeah, at 1, 0, the direction 2 to the right and 0 forward, backward would be the direction of the greatest ascent. So on and so forth for each of these. So now what is the slope at each of these values? I'll show you those in 3, 2, 1. The slope is 2 here at 1, 0, moving in the direction of 2, 0. At root 2, the slope is 4, and then at, in the greatest initial ascent, and then for 0, -3, the slope is 2 root 3. Okay, so one last phenomena. What if we wanted to look at the contour map and then the direction vector at the same time? What would that look like? So the contour plot of a paraboloid is just this basic set of concentric circles. If I were to draw each of these vectors onto this contour plot, you're going to notice a particular phenomena. I'll show you right now. 3, 2, 1. You'll notice that each of these gradient vectors are parallel to their level curves. So going back to that warm-up example that we were looking at earlier, you can see here that if I were to plot the level curve at this moment and turn on the gradient vector, it's perfectly orthogonal. It's perfectly orthogonal at that point in time. It's perfectly 90 degrees. So this is pretty nice. We can utilize this, that the greatest ascent direction is always orthogonal to a level curve on the surface. Whoa. So fellas, if your girl is a collection of partial derivatives, that's a good key feature, shows the direction that's fastest to the increasing f from a certain point, so direction of greatest initial ascent, and is orthogonal to the level curves and surface. That's not your girl, that's a gradient vector. All right, those are the 3 key attributes. Thank you, Victoria, who made this meme. I found it on the internet. Math on.